Good afternoon, dear students. Uh, on the previous lesson, we were working with vector products, and our today topic is linear spaces. This topic is a little bit complicated because it's too abstract, but uh, in next few lessons we will know why do we actually need linear algebra. So its usage. And by the way, what do you remember about linear space? What is it? So the definition. So, does anybody remember? Yeah, it was quite long ago on lectures. Yeah, then you go on.
This is set of numbers that satisfied some conditions. For example, um, need that elements need to be associated that x plus y, where x and y належать,
Belongs.
belongs to L, and L is linear real space.
Yeah, actually, that not only space of numbers, but actually space of real numbers is a linear space as well. But by the way, even uh, set of complex numbers. But yeah, a linear space is also so is the set of any elements. So these elements can be numbers, vectors, matrices, functions, and so on. So different uh, elements that uh, for which we have operation of sum operation, which is commutative. Also, it is associative. So we can put brackets anywhere or just even take them away completely. Uh, Also, we have a zero element in the linear space. We mark it as Greek theta letter. So which properties it has? So if we add the element to this zero element, um, usually we write it in such way that it is so from the left and from the right side. So if we add this element to any element, nothing changes. And also we have the opposite element. So it means that if we add this opposite element, either from the left or from the right side, so we will have a zero element as the result. Also, we have a unit element. So element one. So if we multiply by it, we have x. So it and also we have an operation of adding by the scalar or multiplying by scalar that has as well associative rule. And alpha and beta are just real numbers. Okay. So let's start solving the task. So in our task is so the task one is the next. We need to define if the system of vectors is linearly independent in the linear space of square matrices of given order. So we will solve section A. Yeah, by the way, here, as we can see, this system is called a system of vectors, but a vector in this meaning is like a general meaning. So in generally speaking, vector is the abstract element, and a linear space also called as vector space. So currently we understand matrix by the vector. Who remembers how to check and what does linearly independent mean? Does anybody remember? Maxim, go on.
Uh, as I remember, we need to multiply each of the vectors of this system by some number called alpha, and then add them and see if the system of linear equations equals to zero.
Yeah, so actually what does linear independency means? So that if we have, generally speaking, it means that any elements, so elements from this from the linear space cannot be received as a linear combination of other elements. And the general definition, if so, this equation is true. So this so it equals zero element only if we have only if all alpha elements, alpha coefficients are zeros. So all of them must be zeros. But if someone with some of it are not zero, it means that the system of elements is linearly dependent. Okay, and now let's use this definition. So we need to multiply first matrix by alpha 1, the second matrix by alpha 2. And then what will we have? So alpha 1 here, and here is 0, alpha 2, so we leave alpha 1. And 0 alpha 1 plus 2 alpha 2. Then minus 1 alpha 1 plus alpha 2. Yeah, I will move it a little bit. And here alpha 1 only. And then we set it equal to 0 matrix, capital theta. And it equals, so 0 matrix. Here it's obvious, quite obvious thing that alpha 1 and alpha 2 equals 0. So this cell is alpha 1, this cell is 0. This cell is 2 alpha 2, so this cell is 0. So then we write down so that alpha 2 equals alpha 1 equals 0. So we just write that it's proved that this system is linear independence. Don't forget to write that the conclusion. So why you were doing such operations. So if you write that it's proved, it means that you finished solving the task. Any questions maybe about this exercise?
Can you scroll a bit right? The alpha 1, x1.
Yeah, of course, and I need to zoom out a little bit.
Yes.
Do you see enough? Yeah. Yeah. So, any questions about this recording?
No.
Okay, and about this task as well, as I understand. Okay. Now I have a question for you. Who can tell me how to solve section B? How many alpha coefficients do we have here? Uh, Maybe anybody else wants to take part? Stanislav?
We will have alpha 1, alpha 2, and alpha 3.
Yeah, because we have 3 elements, so we will have to add this matrix multiplied by alpha 1, alpha 2, and alpha 3, and then to compare it with the 0 matrix. Okay, so it will be for your home task, and we will move to the next exercise. So we need to find any basis and define a dimension of the linear space of system solutions. And who remembers how to define a basis for, so how to solve it, how to find find any basis for solutions. So any ideas? So we need just to solve part A, not part B for now. No ideas, yeah? As I understand. Okay, Daniel?
By Gaussian elimination method, we need to get identity matrix or
Uh,
no identity upper triangle.
well, yeah, so we, first of all, we need to solve the system, but what else? What then which steps? Yeah, Gaussian method is suitable for this task. We will use it, of course. And what else? So which the next steps? How to find the basis? Maybe anybody else remembers as well? Okay, then you go on.
Yes, I know we need find free variables and not free variables and basis and due to free variables we need find equation for basis.
Well, so we need to find the general solution. And by the way, how can we define the dimension of linear space in current task?
Other dimensional.
Sorry?
Four-dimensional matrix.
Actually, it is possible, but we can't be pretty sure that four-dimensional. So you define it by the order of matrix, right? But actually, it's incorrect. We need to find the rank of the matrix. And the rank we will define the and so number of dimensions. Okay, let's start solving. So I will write the first row without changes, or maybe better copy and paste it. Will be faster many times. So here I set zeros. So I need to subtract the first number from the second number. So minus 2, 2, and minus 2. And then I multiply the first row by 3 and add and subtract from the third. So 0, then minus 2, 2, and minus 2. 0. So do the same thing. So minus 4, 4, and minus 4. Okay. This these rows can be crossed out. So we will shorten this system. And also I will change the sign here. And divide the second equation by minus 2. So I will just divide by minus 2, so it will look like this. 1, minus 1, and 1. So, who can answer, who can define dimensions, dimension of a linear space?
Second.
Yeah, so order, so dimension of current linear space equals rank of the matrix. It equals 2. So, okay. And now we are going to find the general solution of our system. By the way, who can tell me which variables are bases, which of them are free? Daniel?
X1 and X2 are bases, and X3 and X4 free.
Yeah, so these variables are free. So x3 and x4, and we need to write the solution depending on these variables. So, by the way, why did I write it here? Okay, so x2 equals x3 minus x4, and x1 equals minus x2 plus x3 minus x4. So minus plus minus. So okay, signs are correct. And let's substitute x2 with this part. So minus x, so x3 minus x4 plus x3 minus x4. And it always equals 0, x1. So it doesn't depend on any variable, so it just, so it always equals 0. Okay, and let's write our general solution. So x3, yeah, by the way, let's mark them, our free variables as constants. x3 equals c1, x4 equals c2. It's a good idea not to forget always write that these constants are real numbers. Okay, and then we write our general solution. So x1 is always 0. x2 equals c1 minus c2. Here we write c2. Oh, no. c1 and here c2. So don't confuse them. And who can answer how to find the basis of solutions? How to find the basis in the space of solutions? How many elements must it contain? Okay, so anybody can answer. Maybe Adrian? I haven't heard you for ages.
No, I can't answer.
By the way, the question is basis. So, so what is dimension of this linear space? And it's like a spoiler. Okay, I will answer. Daniil, are you ready to help? Okay, yeah, go on.
We need to find a partial solution.
Yeah, so we need to, but by the way, how many partial solutions?
It can be a lot of partial solutions.
But how many partial solutions form the basis?
One,
No, not
Two.
one. 2 and why 2?
Sorry, can you repeat?
Why? Yeah, Mikola, you were right, but please don't forget to raise your hand.
Okay, because of dimension.
Yeah, so because we have 2 dimensions in our linear space. So the number of elements in the basis always equal to dimension number. So we need to find 2 partial solutions. And the best idea, so the bases are any partial solutions, but we will find a fundamental solution system. So E1, that it will be X, and we set 1 by 1, so one element will be 1 and other elements are zeros. So this, it will be 1, 0, 1, 1, 0. Then E2, The first element is always 0. And then minus 1, 0, 1. And this is the basis actually for this linear space. Of course, any other two partial solutions can be basis, but it's the easiest option to find it. Any questions about this exercise? Raise your hand if you have any questions. It means that no questions. Okay, let's move next. Now we need to find coordinates of geometrical vector x in other bases. So based on these vectors e1, e2, and e3 with prime. You already know how to find how to expand the vector with other bases, but yeah, with the linear, with solving the linear system, but now we will use the other way. And who remembers how to find the coordinates of this vector? Okay, it's a little bit truncated. Any ideas how to solve? So maybe anybody else can answer. Maybe Yevgen? Do you remember?
I don't actually remember.
What about Artem Orlov? Maybe Daria?
I don't remember.
Okay, yeah, so no hands. Yeah, Daniil, help.
I think we can find your coordinates of the vector by equation, because numbers which are near basis E or K are coordinates.
We can do it, but we will use another method. Yeah, but this is correct as well. Okay, does anybody remember how to transform the element? So generally speaking, how to transform from one basis to another? So the way of transition. Maybe you remember something about transition matrix. Okay, so here is the formula which we will use to find coordinates in other bases. So matrix T is the matrix of so transition matrix. To find coordinates of the vector in other bases, we need to find first the transition matrix and multiply it. We need to inverse it and then multiply it by x. From the left side it's important because from the right side it's impossible. So we need firstly to build a transition matrix. Who remembers how to build it? So any ideas? Okay, maybe anybody else remembers how to build it in this task. Okay, Daniil.
Transition matrix will be, we need to find whether the matrix don't equal 0. But
It can, if it equals 0, we cannot inverse it.
yes. So we need to find whether the matrix isn't 0, and after this we find cofactors and stop. This is
Oh.
inverse matrix.
We just need to find, firstly, I'm asking how to find matrix T. So without inversion, or Maxim, yeah.
I'm not sure, but we need to subtract the numbers near I, J, and K vectors and put it in the columns of the matrix T, maybe.
It was incorrect, but it's good that you feel free to answer if even you are not sure about it. So the matrix T will be formed actually by vector by this. So with these vectors written in columns. So it will. So it has the following structure. So vector E1, it will be the first column. So 1, 1, 0.
But I actually meant that, but you said that I was incorrect.
Yeah, but you said something about adding, subtraction. So maybe I didn't understood you correct. I didn't understand you correctly. Okay, but never mind. So yeah, it's good that you understand how to build it. So the second column 0, 1, 1, and the third 1, 0, 1. And now let's find cofactors. So for now, let's just, yeah, not A, but T, of course. Okay, so that's so 1, 1, yes. Minus 2 in minus 1 in power of 2, so just 1 T1 2 equals.
Sorry for interrupting, but don't we need to transpose it firstly?
We can transpose it now, we can transpose it later. It doesn't matter.
Okay, I got it.
Yeah, so actually, do in a convenient way for you, for yourself. T1 3 equals 1 T 2 1 equals 1 T 2 2 equals 1 and 2 T 2 3 equals
Sorry, but
minus
why?
1.
But why T12 is equal minus 1? I think it's 1.
So T1 2, how, so this, oh, I wanted to annotate with zoom, so T1 2, and how to calculate cofactor, so the formula for it.
I got, thank you.
Yeah, so just not to forget. So we need also to multiply the minor by -1 in the power of I plus j. So yeah, don't lose signs. Be attentive. And then T3, 1, 0, -1. Then T3, 2 equals 1. T3, 3 equals 1. Now let's calculate the determinant of matrix T. By the way, we'll clear zoom annotations. So 1 plus 1 and 0, 0, and so 0 for negative side. So the determinant of T is 2. So everything is correct. And now let's build our matrix T inverted. Yeah, don't forget to transpose, of course. So this row will become the first column. So 1, -1, and 1. And this is the second column. 1, 1, -1. And then -1, 1, and 1. So we transposed it now. It doesn't matter when you transpose in such case, but be careful, don't transpose it twice, because it will be the initial matrix. Not initial matrix, but it will be incorrect. Okay, and now let's find x prime, what actually was required. Yeah, and let's write x prime equals T inverted by x. So copy and paste it. And vector x will be written as a column. So -1, 2, 1. And by the way, just maybe for better understanding matrices multiplying by the vector. So here we'll have oh yeah, I will write it firstly, and then you will understand better. So in this cell we will have the scalar product of this row and this column. So maybe it will be helpful for you. So -1 plus 2. Okay, let's write it in detail. In details, -1 plus 2 -1. Yeah, and by the way, we mustn't lose this fraction. Okay, 1 plus 2 plus 1. And this is the scalar product of this. So here we have the scalar product of this row and this vector column. -1 -2 plus 1. here we have 0, 4, minus 2. And finally, 0, 2, minus 1. Any questions about this task?
No questions, I think.
But let me check if anybody raised hand. Okay, no hands means no questions. So what is the next? Yeah, actually task 4. The same things that we were doing in task 3, but more manipulations. So the same, you will have to build transition matrices, find base coordinates of vectors in new bases, which so that you already can do. And now let's have a break, and after that we will work with Euclid spaces and unitary spaces.